story about him that you might have heard. Supposedly, Sir Isaac was hanging out underneath an apple tree thinking, probably partly napping, when an apple fell from the tree and conked him on the head. That's when Sir Isaac had an aha moment. Why did the apple fall down to the ground and not up or sideways? He realized that a special kind of force, which we now know as gravity, was acting on all of the objects on Earth, pulling them toward it. Once the apple became too heavy for its stem to hold it anymore, the gravitational pull of Earth brought the apple down onto Newton's noggin. Newton also realized it doesn't matter how heavy an object is either, whether you're holding an apple or a bowling ball or a feather. If you let go of it, that sucker's going down. We're gonna make a whole video about this later. Basically, he determined that what goes up must come down. Sir Isaac was a pretty smart dude. Okay, so you know that if you jump up, you'll eventually land back on the ground, and you know that an apple dropped down will land on the ground too. But what if you throw something in front of you, or to the left, or the right? To see how gravity will act, pick up the tennis ball or any small round object and hold it in your hand. Let's toss it in the air and watch it fall to the ground. No surprise here. Okay, now pick it up and hold it over your head. Let go and watch it fall once more. Again, not a shocker. Now throw it to your left. Ball down. Pitch it to the right and watch it go down again. No matter where you throw the ball, it's going down. So we've determined that near the surface of the Earth, where we all are, gravity is the cause that produces the effect of all unsupported objects falling down. The ball will go up or to the left or to the right for a little bit, but eventually it's going to be pulled back down to the ground no matter what. Gravity's got a hold on, well, everything. So eventually everything that you can think of can be thrown up into the air and will come back down, even if you throw it to the left or the right or any other direction. That's gravity doing its thing. But when you really think about it, which way is down exactly? I mean, the Earth is round and there are all kinds of things on what we think of as the bottom of the Earth. So how does gravity keep them from falling off? I know a penguin who can answer that question. So, you know that the Earth is round, and you know that gravity is the force that pulls objects down. But if the Earth is round, and there's stuff at the bottom of the Earth, say a penguin in Antarctica, why doesn't gravity pull the penguin down off of the Earth? I mean, does gravity really pull down? When we talk about gravity and we say things like up or down, we don't mean those things in the sense that you're used to. In this case, up just means away from the Earth, and down means toward it. So when you hear people say gravity pulls things down to Earth, they really mean that gravity pulls things toward the Earth. Now think of it this way. Gravity is the force of attraction between any two objects made of matter, right? Well, I have news for you. You're made of matter, and so is the Earth. That means you and the Earth have an attraction to each other. Aw, you guys! Anyway, the scientific argument for gravity is that any object that's on or close to Earth's surface and is made of less matter than Earth will be pulled in by our planet's stronger gravitational pull. Want to do a little demonstration? To show how Earth's gravity can pull an object, like the penguin we mentioned before, toward it, no matter where on Earth that penguin is, all you need is a tennis ball and a rubber band. Oh, and your index finger. Now, let's pretend the tennis ball is Earth, and the rubber band represents the force of gravity. That makes your finger our adorable little penguin, just chilling on the surface of the Earth. Now, stretch the rubber band around your tennis ball Earth and stick your finger under the rubber band. Now try to lightly pull your finger away from the ball. The penguin is trying to jump off the Earth, even though penguins can't fly. What are you doing, penguin? But what happens? Not much. Your finger doesn't get far before the rubber band pulls it back toward the ball, right? And the effect is the same no matter where your finger, penguin, is on your Earth ball. Whether it's at the top or the side or on the very bottom, the same thing happens. The penguin is forced back to Earth no matter how hard it tries to jump off. So, What does this mean?
According to
No, that
space.
was me.
No, I'm
Mama,
before. I have to
what?
work.
It means
I
that
have
no
to
matter
work.
where on Earth an object is, the planet's gravitational pull will draw the object toward it. And that's how you should think about gravity. It's the force that pulls things toward Earth. So basically, we have gravity to thank for the fact that penguins stick to the bottom of the Earth. And I, for one, am grateful. I like penguins. Interesting, huh? When we say that gravity pulls down, what we really mean is that it pulls everything towards the center of the Earth. But what if I want to take a break from the Earth? What if I'm an astronaut and I want to take a vacation on the moon? How can I possibly escape the gravity of the Earth? And if I can, what will happen as I get closer to the moon? I guess there's only one way to find out. You know how many people have actually been on the moon? 12. That's all. But one day, we may go back there. We have a lot more to learn about the moon and space in general. So someday, maybe in your lifetime, we'll send astronauts out there to study and explore. Do you want to be one of them? If you do, let me give you some helpful tips about a little thing called gravity. Because you're going to need to know all about what gravity is and how it works if you're going to escape the pull of Earth and fly to the moon. Now, you already know that astronauts can leave the Earth, but it takes a lot of effort to boldly go where few have gone before. But once astronauts reach the speed called escape velocity, they're able to overcome the force of Earth's gravity and get into orbit around our planet, or head on over to the moon. So this brings up an interesting question. What happens when an object gets away from Earth's gravity, but close to the moon's gravity? You already know that gravity is the force that keeps us from flying off the surface of the Earth, and you know that gravity pulls things not down, but towards the Earth's center. You also know that gravity exists between any objects that have mass, and the greater an object's mass is, the greater the effect of its gravity, or pull, on other objects is. But there's something more. Remember Isaac Newton, the apple tree guy? He determined that the amount of gravitational force, or pull, between two objects also depends on how far apart they are. So the farther away something is from the Earth, the less it will feel the pull of Earth's gravity. And the closer it gets to the moon, the more it will feel the moon's gravity pulling on it. Let's do a little pretending to see what happens to something when it moves closer to an object that has a really large mass, and therefore a really strong pull of gravity. If you've ever made a wish on a shooting star, you've seen the effect of Earth's gravity pulling on an object. Shooting stars, which are actually meteors, occur when pieces of rock break off from a passing comet or asteroid and get too close to the Earth. For example, say this globe represents the Earth and the marble represents a piece of space rock that's flying by. You can see that there's a huge difference in size between the two objects, and if we were to put them on a scale, we'd see that there's a big difference in their mass too. Our model Earth has a larger mass. If the space rock is far away from the Earth, then it can go on its merry way, since it won't be affected by the Earth's gravity. But if it gets too close, then it and the Earth engage in a bit of tug of war. Since both have gravity, they pull on one another. It's not much of a fight, though. The more massive Earth has a much larger gravitational pull, so the rock gets caught in Earth's gravity, and most of the time, it gives us a brilliant streak of light we call a meteor. But what does this mean for our space travelers? Well, when an astronaut ship takes off for the moon and moves away from the Earth, the farther from Earth it goes, the less it feels the pull of Earth's gravity. And as it gets closer to the moon, the spaceship begins to feel the tug of the moon's gravity more. So even though the moon has a smaller mass than the Earth and has less of a pull on the ship than the Earth does, once the ship gets closer to the moon than the Earth, the moon's gravity pulls the ship toward it. And then the astronauts can make a safe landing. So we can make the argument that two things affect the pull of gravity. First, the size of the object. Objects with a bigger mass have a stronger pull of gravity. And second, the distance between objects. The farther apart objects are, the weaker the pull of gravity between them. And the closer together they are, the stronger the pull of gravity. All of this means that when the day comes that you're flying a spaceship to the moon, you just have to escape Earth's gravity and then get close enough to the moon to enter its gravity. Remember that when you're grown up. And you're welcome. If you want to thank me, you could just name a crater or something after me when you get there. So here's what we know so far. Whether on Earth or in space, anything that has mass will exert the force of gravity. And on Earth, everything falls towards the middle of the Earth at the same rate. But hold up a sec. You've probably noticed that if you drop a piece of paper or a feather, it takes longer to reach the ground than something like a rock or a ball. So what's up with that? It's time to investigate. I don't care who you are. If you live anywhere near this planet, then you're no stranger to gravity, the force that affects every object on Earth and beyond. Because of gravity, whether you're an astronaut on the International Space Station or an ordinary, clumsy, earthbound human who happens to drop her books a lot, all things caught in our planet's gravity will, in some way, have the potential to fall to Earth. But objects fall differently, right? Like when I knock a piece of paper off my desk, it takes a lot longer to fall to the ground than if I knock a book off my desk. So what's up with that? Why do things seem to fall at different speeds on Earth? Well, we already know that all objects have mass. They have a certain amount of matter in them, and when gravity pulls on an object, it gives the object weight. Now, a long time ago, people used to think that heavier things fell faster than lighter things because that's what our senses told us. I mean, it certainly looks like the book falls faster than the piece of paper. And why would we expect anything else? That would be like dropping a hammer and a feather and expecting them to hit the ground at the same time. Except the thing I just said about the hammer and the feather, someone did actually try that, and they did both hit the ground at the same time. It just didn't happen on Earth. True story, when astronaut Dave Scott was on the moon in 1971, he did an experiment where he dropped a falcon feather and a hammer from the same height, and they hit the ground at the same time. Now, how can that be? If you drop a hammer and a feather on Earth, the feather would take a lot longer to reach the ground. So, what does the Earth have that the moon doesn't? For one thing, an atmosphere. The gases that make up Earth's atmosphere push against objects as they fall, and the push of the air against the falling object causes friction. We call that friction air resistance. So on Earth, the feather's flat, fluffy shape makes it run into more air resistance than the hammer does. This makes it fall more slowly than the hammer. But since the moon has almost no atmosphere, there's almost no air resistance, so the two objects fell at the same rate. So it seems to me that it's the resistance of air pushing against objects that really affects how fast objects fall. And that means that it's experiment time. But you don't have to go to the moon to do this, so don't pack your bags or anything. All you need are two pieces of paper that are the same size. Crumple one of the pieces into a tight ball and leave the other one smooth and flat. Now drop each piece of paper from the same height, let's say a meter, and then write down in a table how long it takes each piece to reach the ground. You'll see it takes the flat paper longer than the crumpled paper to hit the floor. This is evidence that an object's shape affects how fast it seems to fall to Earth, because the two pieces of paper are exactly the same. They have the same mass. But air resistance makes the flat paper seem to fall more slowly than the crumpled paper.
Recording the space for
So, based on the results of our experiment, we can say, at least here on Earth, objects appear to fall at different rates, not because they have different masses or weights, but because of air resistance, the force that the Earth's atmosphere has on objects as they fall. So there you have it. Gravity is the force that's exerted by everything that has mass, and it's felt by everything equally, even though falling objects on Earth might not always look like that's the case. I mean, if you don't believe me, you can go to the moon and do the old hammer and feather experiment for yourself. Or you can just trust me. If you enjoyed this, check out the rest of our channel and subscribe.
Okay, I hope you learned so much about gravity. Let's talk for a few minutes about some vocabulary words that we can use, right? So, you know that today we're talking about gravity, and in the past, you may have heard someone refer to it as the theory of gravity. But what does this word mean, theory? Most people use theory, the word theory, to talk about something that hasn't been proven, or just an idea that they have in their head, right? Not something that they know to be true. But is that really the way we want to use the word theory? Is the theory of gravity something that has ever failed you? Have you ever been walking along and all of a sudden you just start floating off into the sky because gravity just stopped working that day? I don't think so. A theory is a scientifically acceptable general principle or body of principles offered to explain phenomena. Wow, there are so many big words. How am I supposed to understand what that means? And what it means is a theory is an idea that because of our deep understanding of all other, parts of science, our understanding of physics and chemistry and, the things that we do know for sure about the way the world works, a theory is an accepted idea among scientists of something that is known to be true. The reason we call it a theory is because we can't create experiments to test out that idea without, too many other things interfering with that experiment. So if we were to create some sort of experiment to test gravity, unfortunately, we would always have the Earth's gravity standing in the way. There aren't enough controlled parameters or controlled characteristics of the experiment that we want to do in order to test these ideas that we have about gravity. So there's another word in science, maybe some of you have already learned it in science class, that people really mean when they're using the word theory incorrectly. Do you know what it is? A hypothesis. So at the beginning of the scientific method, when we have a question or an idea about something, we will use information that we already know to come up with a hypothesis, which is an idea or a prediction made in a way that we can test its observable consequences or reactions. Some more big words in that one for some of our younger students, right? And what that means is that a hypothesis is the idea that we can create experiments to test whether or not that idea is true. And a lot of times, what do you think scientists say after they do their experiments to test their hypothesis? They say, I was wrong. And then they come up with a new hypothesis, and they come up with a new set of experiments to test that hypothesis, and maybe they're right, and maybe they're wrong. And that's what it says on our second definition line right here. Experiments are created to test hypotheses, which are then accepted or rejected based on the results. If the results are good, we say, wow, my hypothesis was right, I discovered something new. Or we say, no, I was wrong, and then we move on to the next thing. Now, the next two vocabulary words that we're going to talk about today have to do much more specifically with gravity and the things that we talk about in outer space. And she's already used some of these words, but I just want to make sure that we all have a very clear understanding of exactly what these things mean. Mass. Mass is how much stuff or matter makes up an object, right? So if you have a lot of mass in an object, it's going to be very heavy. And this is not to be confused with volume, which is how much space an object takes up. So if you have some object that has a large amount of volume, but a very small amount of mass, it takes up so much space, but the gravitational effect is not going to be as strong because there's not that much mass, there's not that much stuff, there aren't too many, atoms and other particles that are pulling the other things in outer space towards it. And then we have gravity, and gravity is, in its most simple definition, the force that pulls object with mass towards each other. So we have the Earth, which is very massive, right? It has a lot of mass. And then we have the sun, which has so much more mass than even the Earth. And so they're pulling on each other, right? But because the sun has a lot more mass, it's more that the Earth is going to move towards that. The gravitational force of the sun overpowers the gravitational force of the Earth and pulls the Earth towards it. Another way to think about that is that what else has matter that we know of? We do, right? Our bodies are made up of things, and just like the Earth and the sun, the Earth has a gravitational force, and so do our bodies, and they pull towards each other. But obviously, right, you might know some pretty big people, but none of them are anywhere near as big as the Earth. So the gravitational pull of the Earth pulls us towards it. So these are our vocabulary words for today. And we're going to now watch another video that's going to talk specifically about black holes.
As we've seen over the past few episodes, a lot of really epic stuff happens when a star dies. If the star's core is less than 1.4 times the mass of the sun, it becomes a white dwarf, a very hot ball of super compressed matter about the size of the Earth. If the core is heftier, between 1.4 and 2.8 times the sun's mass, it collapses even further, becoming a neutron star that's only 20 kilometers across. The neutron soup inside of it resists the collapse and prevents the core from shrinking anymore. But what if the mass is more than 2.8 times the sun's? If that happens, the gravity of the core can actually overcome the tremendous resistance of the neutrons and continue its collapse. What force?
So, just to, sort of recap what he was talking about and thinking about these words that we learned about, mass and volume. So when you have not all of the matter goes away inside a dying star, right? Then it's not going to go all the way into no volume but a lot of mass. And then we sort of have this, medium point where it's going to get a lot smaller, but there's going to be a lot more mass inside of that, right? It's going to be a lot more dense is the word when we talk about having a lot of matter in a small amount of space. And then we get to a black hole, which is an incredible amount of matter in an infinitesimally tiny amount of space.
Force can possibly stop it now? It turns out none more force. There is literally nothing in the universe that can stop the collapse. The core of the star is about to go bye-bye. Way back in episode 7, I talked about escape velocity, and it's about to become a major player in the unfolding events of the collapsing core of a high-mass star. In brief, it's the velocity at which you need to fling something off the surface of an object to get it to escape. For the Earth, the escape velocity is about 11 kilometers per second. Get something moving that quickly, and it's gone. It'll never fall back. The Sun, which has much stronger gravity than Earth, has an escape velocity of over 600 kilometers per second. A neutron star, with its immense gravity, can have an escape velocity of 150,000 kilometers per second. That's half the speed of light. Keep that in mind, and let's go back to the collapsing core of the star.
What he wants you to remember is that light is pretty much, by far, the fastest thing that we know about in the universe. Most things don't even come close to going at the speed of light. And so the escape velocity, or how fast you have to go in order to get away from a neutron star or dying star, is about half the speed of light. So I want you to start thinking, how fast do things have to go? Is light able to escape a black hole, or is the gravitational pull so hard that light can't even get out? I may have just given you the answer, but I want you to think about why that is.
As it shrinks, its gravity gets stronger and stronger. That means its escape velocity gets higher and higher. When it's neutron star size, the escape velocity is half the speed of light. But if it's more than 2.8 times the mass of the sun, the core will keep collapsing. When its size drops just a little bit more, down to roughly 18 kilometers, an amazing thing happens. The escape velocity at its surface is equal to the speed of light. And, well, that's a problem, because in our universe, nothing can travel faster than the speed of light. Not a rock, not a rocket, not even light itself. Once the core of the star shrinks down smaller than that magic size, Nothing can escape. No matter can come out, so it's like an infinitely deep hole. And no light can come out, so it's black. We should come up with a snappy name for such an object. A black hole is the ultimate end state for the core of a high-mass star. Whatever happens in a black hole stays in a black hole. That region of space, that surface around the black hole where the escape velocity is the speed of light, is called the event horizon for that reason. Any event that happens inside can't be known. It's beyond the horizon for us. Black holes mess with our concepts of space and time. The math and physics of black holes is incredibly complex, so much so that even after several decades of study, physicists still argue over a lot of their properties. This has led to a lot of misconceptions about them too. All right, let's get this out of the way right now. The sun cannot become a black hole. It takes a stellar core at least about 3 times the mass of the sun to overcome neutron degeneracy pressure. That means the original star must have something like 20 times the sun's mass or more. So we're safe from that particular sci-fi scenario. Here's another misconception. A lot of people think of black holes as cosmic vacuum cleaners, sucking in everything near them. But that's not really true. They have powerful gravity, yeah, but only when you're very close to one. The power of a black hole comes from its mass, certainly, but just as important is its size, or really, its lack of size. If you could turn the sun into a black hole, which you can't, but let's pretend you could, then the Earth would orbit it pretty much exactly as it does now. From 150 million kilometers away, the Earth doesn't care if the sun is big or tiny. We're so far away that it doesn't matter. It gets to be a big deal when you get close.
Right, so what he's saying right now is that because whether it's the sun, a star, or a black hole, the amount of matter and mass will stay the same, but the size changes. We go from this really big star to the center of a black hole. I mean, everything is crammed into literally what we would observe as being no space at all, but all of the density and the matter is still there. So the Earth would just keep going around that area because the gravitational pull hasn't changed.
Remember from episode 7 about gravity, the strength of gravity you feel from an object depends on how massive it is and your distance from its center. The closest you can get to the sun is by touching it, being on its surface, about 700,000 kilometers from its center. If you get any closer to its center, you're inside it. The material outside of your position is no longer pulling you down, and so the gravity you feel will actually decrease. But if the sun were crushed down to about 6 kilometers across, it would be a black hole. You could get much closer than 700,000 kilometers to it, and as you did, you'd feel a stronger and stronger pull as you approached it. So, from far away, a black hole with, say, 10 times the sun's mass would pull on you just as hard as a normal star with that same mass. You can orbit a black hole too, as long as you keep a safe distance between you and it. Orbiting a 10 solar mass black hole would be just like orbiting a 10 solar mass star, except not so hot and bright. Black holes are weird enough without the misconceptions. Black holes also come in different sizes. The kind of black holes I've been talking about have a minimum mass of about 3 times the sun's, and might get as high as a dozen or more times the sun's mass, if the parent star was big enough. We call these stellar mass black holes. If it happens to gobble down more matter, it gets more massive, and the event horizon grows as well. The black hole gets bigger. The idea that huge black holes could form in the centers of galaxies was first proposed in the 1970s, and it wasn't much later that the first one was found in the center of our own Milky Way galaxy. We've measured its mass at a whopping 4.3 million times the sun's mass. And now we think every major galaxy has one at its heart too, and in fact may be crucial in the formation of galaxies themselves. I'll discuss those more in a future episode. Here's a fun thought. What would happen if you fell into one, say a stellar black hole with 10 times the sun's mass? You'd die. But what happens in the few milliseconds before you leave the known universe forever is actually pretty interesting. As we've seen many times in our own solar system, tides are important. They arise because gravity weakens with distance, so a big object like a moon gets stretched by its planet's gravity. The far side of the moon is pulled less than the near side. A black hole has incredibly intense gravity, so the tides it can inflict are serious indeed. They're so strong that if you fell into a stellar mass black hole feet first, the force of gravity on your feet can be millions of times stronger than the force on your head. Remember, even the meager tides of a planet can rip moons apart. When you multiply that force by 1,000,000, you're in trouble. As you fall in, your feet are pulled so much harder than your head that you stretch. pulled like taffy. You'd become a long, thin noodle, kilometers in length, but narrower than a hair wide. Astronomers call this, and no, I'm not kidding, spaghettification. This would happen pretty close to the black hole, just a few dozen kilometers out. If you fell in from a long distance, you'd be moving pretty near the speed of light by that point, and you'd only have a millisecond or so before it killed you anyway, so yay? Note that this is only for stellar mass black holes. Supermassive black holes are far bigger, millions or billions of kilometers across. Compared to that size, the distance between your head and feet is small, so the tides across you aren't nearly as severe. You'd fall in pretty much intact, if that makes you feel any better. But compared to either flavor of black hole, a star still has substantial size, and one that gets too close to any black hole can be disrupted via tides. In March 2011, astronomers witnessed just such an event. In a distant galaxy, a star apparently got too close to a black hole and was torn apart by the ferocious tides. As the star was disrupted, it flared into brightness, momentarily blasting out 1 trillion times the sun's energy. That's how we were able to see it, even though it was several billion light years away. But I've saved the weirdest thing for last. One of Albert Einstein's biggest ideas is that space isn't just emptiness, it's an actual thing, like a fabric in which all matter and energy is embedded. What we perceive as gravity is really just a warping of this space, like the way a bowling ball on top of a bed warps the shape of the mattress. The more massive an object, the more it warps space. Not only that, but space and time are basically two parts of the same thing, what we now call space-time. You can't affect one without affecting the other. Einstein calculated that when a massive object warps space, it also warps time. Someone deep inside the gravitational influence of an object perceives time as ticking more slowly than someone far away from that object. I know, it's bizarre. We think of time as just flowing, and everyone should see it move at the same rate. But the universe is under no obligation to obey our preconceptions. Einstein was right. He was right a lot. This slowing of time is stronger the stronger the gravity of the object is. So your clock ticks a bit slower than someone far away from Earth, for example. The effect is tiny but real, and we've actually measured it on Earth with extremely precise clocks. However, if you get near a black hole, the effect gets a lot stronger. In fact, black holes warp space-time so much that at the event horizon, time essentially stops. You'd see your clock running normally, and you'd just fall in. Bloop! Gone. But someone far away would see your clock ticking more slowly as you fell in. And this isn't a mechanical or perception effect. It's actually woven into the fabric of space. To someone outside looking down on you, your fall would literally take forever. But then they wouldn't be able to actually see you. The light you emit would have to fight the intense gravity of the black hole to get out. And to do that, it would lose energy. This is very similar to the Doppler redshift I've talked about in earlier episodes, and it's called a gravitational redshift. When you're right at the event horizon, just when an outside observer would see your clock stop, they'd also see the light coming from you infinitely redshift. Your light would lose all its energy trying to leave the vicinity of the black hole, and you'd be invisible. And from your viewpoint, buckle up, because this is wow. You'd see the universe speed up, and just as you hit the event horizon, all of time would pass. All of it. And all that light coming at you from the universe would be blue shifted, becoming such high energy that you'd be fried. But since you're about to fall into a black hole, you probably wouldn't care. See? Like I said, wow. Black holes are so strange, with such fiercely complicated math and physics to explain them, that scientists are still trying to figure out even basic things about them. For example, some scientists argue that the event horizon as we understand it may not actually exist, and that when you apply quantum mechanics to black hole physics, you find particles can slowly leak out. We're still new at this, and struggling to understand what may be the most complex objects in the cosmos. Black holes, as bizarre and counterintuitive as they are, keep popping up from here on out as we poke our noses into more and bigger astronomical objects. While they may seem scary and weird, and let's be honest, they have literally shaped most of the objects we see in the universe. Today you learn that stellar mass black holes form when a very massive star dies and its core collapses. The core has to be more than about 2.8 times the sun's mass to form a black hole. Black holes come in different sizes, but for all of them, the escape velocity is greater than the speed of light, so nothing can escape, not matter or light. They don't wander the universe gobbling everything down around them. Their gravity is only really intense very close to them. Tides near a stellar mass black hole will spaghettify you, and time slows down when you get near a black hole. Not that this helps much if you're falling in. Crash Course Astronomy is produced in association with PBS Digital Studios. Head over to their YouTube channel to be sucked into even more awesome videos. This episode was written by me, Phil Blake. The script was edited by Blake T. Testino, and our consultant is Dr. Michelle Fowler.
They
So
were
that was a
using
lot of
kids'
information
YouTube?
about black holes, right? But I think based on the vocabulary we talked about and his really, really great explanations,
Why
hopefully
would they be
you have a
using
better understanding
kids'
of
YouTube?
what they are and how they work. Now, the last thing that we have to talk about today is related to this idea that he mentioned about the fabric of space or space-time. And the idea that we're going to talk about related to that is this concept of dark matter. And if you remember back to Thursday, dark matter played a really big part in that video we watched about how far humans will actually or would actually be able to travel in space if we can leave the solar system, if we can leave the galaxy. How far, how much more, how much further would we be able to get before we get stuck? And so we're going to watch this video of someone singing a song to us about dark matter, and then we'll be near the end of our session today, and I will open it up for more questions.
Come on, Gordon.
No Skills Entertainment. Space stuff. Dark matter. Look up in the sky, there's the moon you see. There's some stars, there goes Mars, Pluto, R.I.P. Those are just a few of the things in our galaxy. All of it's held together by tons of gravity. But what if gravity wasn't strong enough? Everything in the universe is held by some other stuff. Some other stuff you cannot see with the naked eye. Some other stuff that doesn't shine when it's hit with light. It seems that we have ourselves another mystery. So let's travel back in time to 1933. Fritz Zwicky was observing the coma clusters, and this would lead to an astronomy adjuster. He was measuring those galaxies' mass, and based on the observed mass, they were moving way too fast. There had to be something else to cause such speeds. Apparently, we had missing matter missing from the galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. The center of our solar system is the sun. The closer that you get to it, the stronger gravity becomes. Close planets revolve fast, far planets slow. It's the gravity to distance to speed ratio. So if the coma clusters are moving too rapidly, maybe something invisible added to its gravity. Decades later, based on further observations, dark matter is the name of the situation. Well, what is it? No one knows for sure. An accurate description remains unsecured. Search for answers activated. Simple yet complicated. Constantly investigated. Mysteries generated. Matter or a particle? Guess it's hypothetical. Research problematical and others very skeptical. But for now, that's just how the story goes. It's a known unknown. A thing we know but just don't know. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. There's a lot of concern with the dark matter case, as it may be 80% of the stuff in space, holding the stars together like some cosmic paste. Scientists are in a rush of proof. Space race. Let's talk about some of the theories that have generated dark matter. Maybe how our universe originated. Following the Big Bang, the universe formed after, and it may have come together with the help of dark matter. String theory mentions dimensional planes, stacked on top of each other like some video games. There's universes above us, but we cannot see them. Dark matter may be the gravity that's in between them. So if you're on a quest for the dark matter reward, you'll have to explore 11 dimensions or even more. Now I understand if that is hard to believe. The universe is like bread and dark matter is the cheese. What if I said there's something funky with the universe? For all the time that human beings roamed the planet Earth, There was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings on the planet Earth, there was something we couldn't feel and couldn't see, oblivious to dark matter in our galaxy. What if I said there's something funky with the universe? For all the time that human beings on the planet Earth, there was something we couldn't feel and couldn't see. Or maybe we just don't understand gravity. Maybe you're right about that.
Okay, interesting thing he ended his song with there, right? Is maybe we're going to learn something and then find out that everything we thought was true is no longer true. And then what is the thing that scientists are going to have to say? I was wrong. Okay, so quick review. Let's first go through some of the words we talked about today, right? Gravity is the force that pulls objects with mass toward each other. Remember, we watched that video about gravity on Earth, why things fall towards the Earth, and how the planets are pulled towards each other, but most importantly, how they are pulled towards the sun. Mass, how much stuff makes up an object, right? We also talked about volume, which is how much space an object takes up. And then what do we know from these two words is that a black hole has a lot of mass, but it doesn't take up that much space. So the gravitational pull is really, 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 really strong. We talked about theories and hypotheses. A theory being something that we have a lot of evidence to support this idea that we have, but we cannot create an experiment to prove that it's true in that way. A hypothesis being the idea or prediction that we come up with based on information, but we can run experiments to find out whether or not they are true. And a lot of times, again, what do scientists say after they run those experiments? I was wrong, and then they start all over. Okay. So just a reminder, before I open up the chat again, we need to keep the questions on topic. We need to be polite and respectful, and the questions need to only happen once, right? So we're asking questions, we're not making statements. This is not story time. We're not going to talk about, what we did over the weekend. We're not going to talk about some other idea we had, unless it is a question that can be asked about the things that we've been talking about related to space and gravity, black holes, dark matter, all that kind of stuff, right? So if you have questions about how that stuff works, ask them now. I'll do my best to answer them today, and if not, I will try to keep learning more and bring you more information next time on Thursday. Do other planets have gravity? Yes, they do. Remember, I said that anything that has mass has gravity. So planets are made up of stuff, they have mass, and therefore they also have gravity. If you were to travel to Jupiter or Neptune, they have different amounts of gravity, but yes, they do have gravity. Antimatter. I will read about antimatter and get back to you. How does dark matter work? From Griffin 5. Dark matter is one of those things, it's sort of like in the beginning stages of our ideas. It's maybe more of a hypothesis at this point. Scientists don't really know what it is. It's really hard for us to interact with it. That's a good question. Hopefully, maybe someday you'll be the person who finds that out for everybody. What is mass made of? So anything that you can think of, it's made up of the elements of the universe, which are made up of atoms, and then there are subatomic particles like electrons and protons and neutrons that come together and have different charges, and they behave in different ways. And then there's stuff even smaller than that I don't know too much about, but anything that you can think of that has mass. Can you talk about the recent life on Venus discovery? If not today, then later. Yes, I will talk about it a little bit today, and then I will talk about it more later. So when scientists find evidence of possible life on other places, we're usually talking about very, very, very basic forms of life. We're not talking about civilizations like human, with animals running all over the place and all sorts of diverse plants and stuff. Usually we're talking about, some very small, like microbes or cells or something like that. Cells are pretty advanced for what we're even talking about, that probably exist in water, or maybe we just see evidence of some things that existed a long time ago, but we're not 100% sure yet. And I will find out some more information for you and talk about that another day. Do wormholes exist or no? Wormholes are, this possible idea that inside a dark hole, a black hole, there would be a wormhole that would kind of rip through this fabric of time space and could spit you out on another end. And if that were the case, we could use black holes to do intergalactic travel, going really, really far distances across the universe. But one thing you have to remember is what happens to stuff and what would happen to our bodies if we were to go into a black hole, right? It gets totally transformed in the way all of that stuff exists together. So even if we could get the physical stuff that makes up our bodies through a black hole, we probably would not survive. Can a black hole push things out instead of in? I've never heard of that happening, and I don't think so, because remember, there's so much mass that it's just pulling. So we don't know of any type of situation where it would be repelling things other than the first sort of explosion after the death of the star, right? Where all of that energy is being, immediately pushed away. What is the link to the last video? I'll send all of the videos in a message on the Varsity Tutor website. So a couple people are asking about gravity on Jupiter. And an important thing to try to understand is that not all of the planets are made up of the same stuff that Earth is made up out of. So on a lot of different parts of Jupiter, it's really just made up of a lot of gas being stuff like air, right? Like stuff that you can't just grab with your hands. Maybe you can bottle it into a container. We can do different things to it, but it's not stuff that is really easy to, pick up and move around. But on some parts of Jupiter, the matter that makes it up is very dense. So on some parts of Jupiter, the gravity in that towards that area is very strong, and in other parts, it's not as strong. Can Earth get sucked into a black hole? Not during our lifetime. They're all way, 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 way too far away. Earth exists sort of on the very outer edge of the galaxy where we live. So any black holes in our galaxy are way, way, way too far away for us to ever get close to them. How long does it take for a black hole to form? It is my understanding that it takes billions and billions and billions of years, just a really, really long time. So long that we couldn't really even imagine how long that would take in our own mind. What is Earth? Earth is the planet that we live on. How many galaxies are there? A lot. I mean, they're discovering new ones all the time. How do astronauts land back on Earth? They crash. Really. They usually, I think they find a place to safely land in the water. Will the sun ever go out? Yes, but like I said before, someone was asking about how long it takes for a black hole to develop. Billions and billions and billions of years. It's going to be a really, really long time. Okay, it looks like maybe we've gotten a little off topic with a lot of these questions here. So I will do some more reading about some of the questions that I wasn't able to fully answer today, and I'll get back to you on Thursday. I will see you at 4:30 Eastern, 3:30 Central, 2:30 Mountain, 1:30 Pacific on Thursday afternoon. Have a great rest of your day.